And lesson 2.4, day 2. We're on to the third video for the day. And with this, we're going to look at, you pronounce this name, Descartes, French person. Descartes' Rule of Signs. This is actually quite useful in just a couple of circumstances. What Descartes' Rule of Signs does is it can be used to build what we call a P&I table. This is what one looks like down here. That's a P&I table. This will do is it indicates how many positive, negative, and imaginary zeros a polynomial could have. Okay, which different combinations you could have. And you do it simply by just counting how many times the sign changes as you hop from term to term in your polynomial. If you're looking at f of positive x, that's going to give you your positive real zeros. You just count the number of sign changes for f of positive x. Then there's this weird bit, I'll talk about that in a second. And then if you want to find out how many negative real zeros there are, you look at your function with negative x in it. And again, just count the sign changes. Now, what this all less by 2 means. If you count the sign changes and it changes from a positive sign to a negative sign to a positive sign to a negative sign, if there were 5 changes, say you counted 5, you've got to consider everything that's less by 2's. You could have, say, 5 positive real zeros, or 2 less than that would be 3, or 2 less than that would be 1. So you could get 5 or 3 or 1. Would we go less than that? Would we say, or negative 1? Can we have negative 1 of something? Can you have negative 1 pineapples? No, you can't. So we stop at 0. You can have nothing of something. You can stop at 0. Okay? So it's probably easiest done by an example. So pause the video, write these notes out. They're useful notes. And then let's go on with an example. So in this one, describe the possible real zeros of the function. And how we're going to describe them is we're going to draw a P&I table. Positive, negative, imaginary. That's what that stands for. The first thing we're looking at on this is we have a polynomial of degree 3. It has 3 zeros. But they could be any combination of positive, negative, or imaginary zeros. But if we added up the number of positives, the number of negatives, and sum them with the number of imaginary zeros, we would come to a sum of 3. Now these tables, sometimes they go on and they have multiple lines because there's multiple possibilities. On this one, we just need, I know I've already done this example, there's only 2 possibilities. The first thing we look for is how many positive real zeros there'll be. And all you do is you count your way from term to term, how many times you switch. This is a positive, so we go from a positive to a positive, no change, to a positive, still no change, to a positive. This has no sign changes, and that is the most useful thing to know. It's really useful, because it means it's got no positive real, I should write that as a word, shouldn't I? It's got no positive real zeros. So, for instance, if I wanted to find the actual zeros of this, I'd know there were 3. I can always find them if they're something that's quadratic. But with the degree 3, I sometimes can factor it. This one I couldn't. You couldn't factor this by grouping. It would be disgusting. It just wouldn't work. So I've got no way of factoring it. So what I'd have to do is guess and check to find 1 0, then divide that 0 out till I have something quadratic. Then I could solve the quadratic to find the other 2. So I'd have to guess and check to find one. And how I would guess and check is I'd make my list of all my p's and like, oh gosh, there'd be loads of q's. There'd be loads and loads and loads of them. So my p's divided by my q's would be plus or minus all the factors of 6, which are 1, 2, 3, and 6. And get each of those and divide them by all the factors of 12. So I'd have to do 1, divide them all by 2, and skip that 1, can skip that one. Then I'd have to divide them all by 3. Oh gosh, you get the idea. But this would go on and on and on. There'd be a long, long list of P's and Q's, lots of things to try. What Descartes' Rule of Signs has told me are there are no positive real zeros. So it's cut my work in half. When I'm guessing and checking, I wouldn't have to look at any of the positives. None of them are going to give me a 0. All I'd have to do is try the negatives. So it really can cut down on your work. Okay, hopefully this one's got some negative zeros. Let's find out. How use Descartes' Rule of Signs. Let's move this work out of the way. Okay. How you use Descartes' Rule of Signs to find negatives is you have to do your function of negative x and count the sign changes in that. Now remember, if you have something raised to an even power, if you have negative x raised to an even number, it's the same thing as just positive x. So you don't change the term it's in. But if you're raising something to an odd power, you are going to flip the sign of the term it's in. Because it's going to equal a negative. So you're multiplying by -1. So as I go through my polynomial, let's remove all that stuff that's on it. I've got 12x to the power 3. 3 is an odd number, so I'm putting in negative x here. It would make this be negative. It was positive, I'm changing it to a negative because that 3 was an odd number. When I'm looking at my x squared term, that's an even number. That was plus, it stays as plus because this 2 is an even number. It doesn't flip it. Then this is x to the power 1, an odd number, so I flip what's at the front, was plus, and I write minus instead. And then this one, there is no x in it, so it just stays the same as what it was. Now we have to go along and count our sign changes. I'm going from a negative to a plus, so now I'm just counting. That's one sign change. That was another one, so the 2 sign changes. That's another one. I've had 3 changes in sign as I've gone along the polynomial. That tells me, I'm looking at the negative ones here, so that tells me I have 3, or 2 less than that would be 1. I can't go 2 less than that again, so just 3 or 1 negative real zeros. So now let's fill in the chart. In the positive column, all I'm ever going to have is 0. There are no positives. And if I had more rows in my chart, I'd fill them all in with a 0. And I'd have to do every combination of the different possibilities, the positives, with the different possibilities with the negatives. So this would be 3 or 1. Now, on each row, if there were no positive real zeros plus 3 negatives, there couldn't be any complex because the sum of these has to equal 3. If I had no positives, 1 negative, there must be 2 complex. How I could use this to help me is not bother looking for any positives. If I found 2 negatives, I know the third would be negative as well. Okay, that's how you could maybe use that information. So let's practice some. If you'd like to try these, pause your video, give them a chance, and then come back and see me go over them. So on this one, positive. Let's count the sign changes. Plus to minus to plus. Okay, I had 1 change going from plus to minus, and then I changed back going from minus to plus. So I had 2 changes, which means I have 2. Can I get less than? Can I reduce that by 2? Yes, 2 or 0 positive real zeros. So in my table, I've got 2 and 0, and maybe if I have more than one choice with the negatives, maybe I'll have to do 2 and 0 again. We'll see. Okay. Now I'm going to do the negatives. To do the negatives, I write up my polynomial again, and if it was to an odd power, I flip the front. So this would be negative x cubed. This is even, so that stays the same. This is odd, so I have to flip this minus to a plus, and then I leave plus 17 as plus 17. So how many changes have I got? I'm going from negative to plus, that's one change. No more, no more. So I only have one change, which tells me my polynomial does have, I have to find one negative real zero. Okay? So this one's not as useful as the last example, because if I was looking for zeros using P's and Q's, I would have to try both plus and minus 1. The only other factor of 17 is I would have to try, if neither of those worked out, I'd have to try plus or minus 17. Ugh, I'd hope plus or minus 1 would work. Okay, so I only have one real zero, so one real negative, so I only have one, so I didn't need this extra combination. Okay, I have to have 3. These lines, each row must sum to 3. So 2 plus 1 already equals 3. This combination could have no complex zeros. And in this combination, 0 plus 1 has to add up to 3. So I must have 2 complex zeros. And moving to the last example here. We have positives. We've got 1, 2, I don't know, let's count those again. 1, that's changing, negative to plus, that's 3 changes. Okay, I've got 4 changes here. Wow, that's a lot. So I have 4, 2 less than that would be 2, 2 less than that would be 0, positive real zeros. So my table would go 4, 2, 0. And if there was more than one option with the negatives, I would have to repeat that. The way my table's set up, I'm assuming that that's not going to happen with the negatives, but we'll see. Just set it up just in case. For the negatives, I need my function of negative x. Oh, look, I wrote that wrong last time. That should have had a negative there. Okay, this equals, that's an even power, keep it negative. That's an odd power, flip it. That's an even power, leave it the same. That's an odd power, so leave, flip it. Flip it, minus 6x, and then I've got minus 9 at the end. So as I go along, no change, no change, no change, no change. Ah, that's useful. We have no changes in sign. So we have no, we were looking at negatives, no negative real zeros. So in the n column for negatives, by each of the combinations with positive, and I didn't have, say this had come out with 2 or 0, there'd been 2 sign changes, I would have had 2, 2, 2, 0, 0, 0. I would have had to draw 6 lines. And these are all a bit boring, these examples. Now, what does each line have to add up to? Each line, if you look up here, this was a polynomial of degree 4. So the sum, as we're adding across, has to equal 4. Oh my goodness, that's big, isn't it? Okay, so this would mean that this line here already adds up to 4, so that's going to be 0. The second row only adds up to 2, so it need to have 2 complex zeros. And the last one, oh, that would be horrible. Oh man, that would be horrible, having to find 4 complex zeros. So those would be your possibilities. Moving on. Find the polynomial with the given zeros. Oh, these are easier than the ones we've already done if you look at them. Some of them look a little ugly. So I'll just find, if you want to pause your video and just practice. Here, let's go. This would be x minus 2. X minus negative 3 would be x plus 3i. And remember, this one would come in plus and minus form. There'd be a pair of them. So I'd have x minus 3i. Okay, we want it partially factored, so let's do x minus 2. Difference of squares, this would be x squared minus 3i squared, which is 3 squared I squared. So this would be x minus 2, x squared. 3 squared is 9, I squared is minus 1. So we're subtracting negative 9, which is the same as adding 9. That's this one. And number 13. Okay, so we've got a 0. This would be the factor is x minus 0, which is simply x. Our next factor, this one, would give us x minus 3. This one here would give us x minus I, which would be x plus I, yuck. And this one would come in plus and minus. They come in a conjugate pair. And if you're subtracting that, that would give you x minus I root 2. So we've got to multiply these last two factors here together to get rid of those. In partially factored form, we mean no square roots in your answer and no imaginary parts in your answer. So we've got x minus 3, and then we have got, this is difference of squares again. Same beginning, same end, with a plus in one and minus in the other. That multiplies out to be a squared minus your b squared. I times the square root of 2 squared. So this would be x minus 3, x squared. Think about minus, you've got I squared and root 2 squared, and you're subtracting it. So you're subtracting negative 1 times 2. You're adding 2. One more screen and we're done for the day. So if you'd like to try these, and pause your video, back, and I'll do these ones. This is a 0. It has a partner. It's part of a conjugate pair. Remember, we're building a polynomial. We need factors. And your factor is going to be x minus the 0 that you've written. So my polynomial on this one is going to be x minus that first one, which would be minus 1, distribute that minus I root 3. And then x minus 1, distribute that to that, that would become plus. Minus 1 plus I root 3. So this would equal, we've got difference of squares again. We have a minus here and a plus here. Same beginning, same end. The beginning is your a. So we would have your a squared minus your b squared. Your b is the end part, a bit after plus minus. So this would give you x minus 1 squared, multiply it out. If you need to do it on the side on a piece of paper, do. X squared minus 2x plus 1 minus, the I squared would be negative 1. The root 3 squared would be just 3. So you're subtracting negative 3, which turns into adding 3. That's your answer on this one. And the second one. Right, this guy's got a partner. Ooh, I wish I could move that line out of the way. Group that and make it small. There we go. Move it out of the way a bit. Okay. So this one's got a partner, and his partner is going to be, they come in a pair, 2 minus the square root of 7. Ooh, yuck. So our polynomial is going to be x minus the 0. It's be minus 2 minus root 7, x minus 2, and don't forget you're subtracting all of this, so that would turn into plus there. So I've written that on a 0. I don't like that in there. Fussy. So we've got difference of squares again. Now there's a totally different way of doing these products, multiplying these out and getting the answer. It's called sum and product. And I don't teach it. I don't like it because it's something you just memorize. You do this, you do that, add this together, multiply those, and there's your answer. And I don't like it because students still get it wrong, even though it's quite simple. And it's just memorizing. You're not actually working with math that you understand why it's working. I hope you understand this. Difference of squares. We used a lot during the year. So I've got difference of squares. My A is x minus 2. My b is the square root of 7. Difference of squares says a squared minus b squared. So this is going to equal x minus 2 squared is x squared minus 4x plus 4. Then I'm subtracting the square root of 7 squared, which is 7. This time there's no I being squared, so I'm not going to change that minus to a plus. Wasn't complex. All I've done is I've said the square root of 7 squared is 7. That's what I've done there. And I'm subtracting it because it's difference of squares, yeah? Always subtracting. If you're squaring an I, you're multiplying by a negative, so you end up adding if it was a complex number. X squared minus 4x plus 4 minus 7 is minus 3. So here's our answer to that one. And our last one. Okay, this would be polynomial. This gives me x minus 0, which is just x. Ooh, and this guy's got a partner. It's the bit in front of the square root that comes in plus or minus. This minus is minus for both of those in that partnership. So my zeros are 0, minus 3, minus root 2, and minus 3 plus root 2. You only see the change between the minus and the plus in front of the irrational part. It's coming from x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. When you use solving something that's quadratic like that, if you ever have anything that's irrational or imaginary in front of the imaginary or irrational part, in front of the square root, this is where your conjugate pair is coming from, why you have a plus or a minus just in front of the square root. It doesn't change here, it changes here. Okay, so this would give us, that first 0 just gives us x as a factor. Then we'd have x minus this lot. If you're subtracting a negative, that's going to be plus. If you're subtracting this, that would turn into plus. This would turn into plus. Ooh, I haven't got room to write this. I'll write it smaller or something. And then this, the second one, the one I wrote up here, we're subtracting that. The x plus 3, and this plus here, we're subtracting it, turn into that. Okay. So again, we've got difference of squares. Here is where they're different. This is your a plus b, this is your a minus b. And when you're multiplying those together, we've got the x on the outside, so don't forget him, we have x times your a squared is x plus 3, has to be squared, and it's a squared minus your b squared. Our b is the square root of 2, so we have the square root of 2, which needs to be squared. This gives us x times x plus 3 squared would be, multiply it out by FOIL, x squared plus 6x plus 9. Then we have this subtraction, and then we have the square root of 2 squared, which is just 2. So our answer for this one is x times x squared plus 6x plus 9 minus 2 is plus 7. And on this one, it wouldn't really take much work at all. That wasn't part of my answer, it was just notes. It wouldn't take any work at all to actually finish this off totally and get a fully expanded polynomial. It'd be x, distributing that x cubed plus 6x squared plus 7x. It's not even just partially factored, that one's fully multiplied out. If I wanted it partially factored, this would be partially factored. Okay, and that's it for this lesson.